either sequentially or in parallel. I'm going to build the hash partitions for R and the hash partitions for S. So everything where the hash function is J is going to be put inside partition R sub J. Everything where the hash function is J is going to be put into S sub J. Can there be any matches between R sub 17 and S sub 3? Can the joint columns be equal between R17 and S3? I don't think so, because a hash function is deterministic. H of 79, whether I'm picking it up from R sub I or S sub J, H of 79 is going to be a given value. Now, there can be puns. Two different things can be put into R sub 3, even though the values of R sub I aren't equal. So when I'm putting things into, R sub 17, I'll be putting things that have different values into R sub 17. But anything that matches between R and J, they gotta be put into the same subscripted partition. Capital R sub 17 and S sub 17, any matches that I need to make will be in both 17s. I'll have to look at capital R sub 1 and capital S sub 1, capital R sub 2 and capital S sub 2, all the way up to whatever the value is, R sub 50 and S sub 50. But there can't be a match where they're in different partitions because the hash function is deterministic. Everybody cool with that? Really important point. I used it when we did the block nested loop join. The hash functions are deterministic. The matches have to be in the right place. Okay? So I've finished going ahead and I've created my partitions, B-1 partitions of R and B-1 partitions of S, using exactly the same hash function. Everybody cool? Question? Don't want to make a hash of it. Well, I do want to make a hash of it, but not. All right. And now there's the match phase. I'm going to read in one of the partitions of R, let's say R sub 17. And then what I'm going to do is I'm going to use a hash function, which my similar lack of imagination, I'm going to call H2, the important thing being that H2 is not the same as H. I'm going to ask you why in a second, but let's see what's going on. And now what I'm going to do, very similar to the block nested loop join, is I'm going to build a hash table based on R sub 17. And then I'm going to read in block by block the things inside S sub 17 and find all the matches. But only for the tuples in S sub 17, not for everything in S, which is what I did with the block nested loop join. I'm going to take S17 and I'm going to look using H2 for the matches on the join column about what's going on. So I'm going to hash the join column where, again, there can be a whole bunch of different puns that end up existing. And I'm going to find all the matches. Question?
So this second phase, you're using the partitions that have been created
in the first phase.
Hashing in the first phase.
Correct.
So everything already matched through the first H.
It matched on the first H, which doesn't mean that the join columns
Right.
match because, again, there can be puns.
Right. Okay.
As you know, I love puns, but that doesn't mean that just because things have the same hash function value, the join columns may not be equal. Now, why am I using H2? I have a perfectly good hash function H around. Why not just use H again? Somebody want to tell me why I don't use H?
They're already.
Your hand name answer. There are lots of people who seem to have it. Go ahead. Give me a hand name. Go for it.
Jazel, is it because you can use the second hash function to see if they hash into the same bucket?
I can, but why not just use H?
Because they might not have been the same, but they hashed into the same bucket with H. So if you were to use the second hash function,
One of the definitions of insanity is doing the same exact thing and expecting a different answer. Everything that's in R17 or S17 has the same value for the hash function. What I'm trying to do is to separate out things Because again, there are these puns. There could be 1,000 different things that have the value 17 for the hash function. I want to separate them out so that I can figure out which things match with which things. Using the exact same hash function, the hash function is just going to be 17 for everything in R17 and S17. Doing it again, 17, 17, 17. Gets kind of repetitious and dumb. It doesn't give me any value. That different hash function will allow me to separate out the things that have different values so that I can find the matches. Especially if I'm, again, picking a good hash function. So it's the same thing that I did with the block nested loop join, and again, I can be clever about having shadows for it. I read in, I go ahead and I use B-1, B-2 buffers for R, and I find all of the matches. And you know, I can go ahead and I can do this. And if I'm lucky and smart, all of my R sub I is going to fit inside memory. So I only have to go through the S tuples once. So the build phase, I create my R's and S's using the exact same hash function H, because I know that there can only be matches when the hash functions agree. Hashing on the join column, because I'm only looking for matches. Second phase, I use a different hash function, critically important, because there's no reason to get 17 again and again and again. It's not going to differentiate. I use a different hash function so that I build a hash table with my B-2 blocks inside memory for R, and then I go through the S's and I find that things are different. But now I've divided by the number of partitions I have. I don't have to go through everything at S. I only have to go through the things in the individual partition. Question?
So couldn't you have what prevents you from having double puns?
What, from having?
Double puns?
Where that could end up happening. It tends to be relatively, unlikely, but you know, it could end up happening. But I'm about to go into something that partially addresses your question in detail. We'll see how the thing goes. So first of all, we'll do a little analysis, and then I'll address. In line with what you're saying, let me point out the following thing. So I'll point it out on this slide rather than later. What's the problem I'm solving in problem 2, in the match phase 2? It's exactly the problem I started with, which is doing a join. To begin with, I was trying to join R and S. Now I'm trying to join R17 and S17. Exactly the same problem I had before. And so, what we're going to get to, but since the question was asked, I want to mention it right now. If R17 and S17 are big, and for example, I can't fit most of R, let's say, inside memory, I could do the same trick again, recursively. Maybe some of you got it, some of you are shaking your head. If not, you may be able to get it on the next slide. The problem of doing the join of R17 and S17 is exactly the problem I started with when I was trying to join R and S. Except that I have a bunch of partitions, and so I can focus more on a subpart and only have a smaller thing fitting inside memory. And if it turns out that R17 and S17 are too big because they're skew and too many things with too many multiple puns, I can recursively do the same darn thing again. But let's see what's going on. The number of partitions is going to be less than or equal to B-1. Why? Well, basically, that's how I picked my hash function, so it only had B-1 values. So that's pretty clear. And you'll see why I picked the number B for this coming forward. And basically, if I'm doing things right, the number of pages of R divided by the size of the largest partition of memory, the largest partition that I have, is also going to be less than or equal to B-1. So again, what I can do is I can fit, pages are divided by the size of the largest number of pages to be held in memory is less than B-1, so that I can go ahead and I can fit things. Again, I can fit things inside memory to be able to fit the R sub I inside memory. So again, if that's true, that's less than b minus one. And with the unreasonable assumption that I have uniform size partitions, right, and making k as big as possible, then k would be b minus one, and pages of R, right, so again, k is the number of partitions, pages of R divided by k is gonna be the size of the partition inside memory, if things are uniform, right? K partitions, if things are uniform, I end up having pages of R divided by k is the size of each partition, if things are uniform. So let me say it one more time, right? Right, k is less or equal to b minus one, the number of partitions, it's gonna be b minus one. Pages of R divided by k is gonna be, if things are uniform, if the sizes of the partition are uniform, the size of each individual partition. What this says is that, right, if I have k equal b minus one and pages of R divided by k is less than b minus one because I'm trying to fit the partition inside memory. Okay, okay. So basically, I end up having then easy calculation. B minus one squared is greater than the number of pages of R, if this is working, which implies that B has to be greater than the square root of M, that is, B is greater than the pages of R. That's basically B minus one squared is greater than pages of R, then B is greater or equal to the square root of pages of R. So basically, if you can pick B, which is more than the square root of pages of R, pages of R could be big. Square root of pages of R might not be that bad. But what trick am I going to use? 1 second. What trick am I going to use before, if things are too big? I can recursively do this multiple times and get the thing down. Because then all I'll need is be greater than pages of R sub 17. I can do this multiple times if I have skew and things are of different sizes. Again, building the in-memory hash table, it's going to be more than the number of pages inside, because the hash table takes a little space. So again, just to finish off this slide, if the half function does not partition uniformly, here we assumed that everything was pages of R divided by k. If it doesn't go ahead and partition uniformly, some partition may not fit into memory. Here I got 10,000 tuples. Here I only got 1,000 tuples. So it's not uniform. Something may not fit inside memory, and I can recursively use hash join to be able to deal with that. There is a situation in which this is not going to really help me that much. If everything has the same value, hashing again recursively. Remember insanity? If everything has the same value, no matter how times I recursively do this, it's called recursive stupidity. I'm going to be doing exactly the same thing again. Basically, that's going to end up being a problem. Now, you had a question.
Yeah, I'm confused about why the number of partitions k is number of partitions is both equal. If the number of partitions total and the size of the largest partition are the same value.
Okay. But the reason the number of partitions k is less than or equal to b minus 1 is that, let's just go back to the previous diagram. What I was doing was I wanted to have as many partitions as possible. I'm reading a block of R, I'm putting things into the partition. When a partition gets full, I'm going to end up writing it out. So if the value is 17, I'm going to be putting it into R17. So I'm going to be doing the same trick. As R17 fills up, I'll write out the buffer to disk. And again, I'm not using the double buffering trick. But when a buffer fills up, I'm going to write out that buffer to disk. So again, the most that I can deal with is b minus 1, if b is the number of blocks that I have. So that's where the b minus 1 comes from for that. Why do I want the other thing to be less than k minus 1? Because of what I'm doing here. It's going to be less than b minus 1. It's the same reason I did it with the black nested loop join. I'm reading in the things from S, 1 block for this. I'm creating an output, 1 thing for this. So this is equal to b minus 1. This is going to be less than b minus 1. It's basically because I only have b buffers altogether. Okay, and so the size, if I want all of R17 to fit inside memory, then it has to fit into b minus 2 blocks, plus a little overhead from hash table. That's all that's going on. questions about this? It may be that pages of R is not, is too big. The square root of the pages is not gonna have this relation that B is greater than the square root of pages of R. But then I can recursively do this. The other point to observe is that I get to pick which is the inner and which is the outer. So I can pick things, if S is more uniformly distributed and smaller than R, then I can pick the other thing to be the inner. So basically, what's the cost of doing the Grace hash job? Oh, yeah.
So you know how you mentioned you might need to recursively break up one of the hash indexes? So
Yeah, one of the hash partitions.
right, so
It's not an index.
sorry. So for each time you do that, I guess you would need a different hash function.
Darn right.
Right, so like.
Yeah, I
you
may
do
need
it 5
H3,
times.
H4, etc. Repeating the same hash function is not gonna help me because things got put together because I agreed on the hash function, the previous phase.
Okay, so none of them can use the same output.
Not unless I wanna have bad separation.
Right.
The whole point again is that reusing a hash function is useless. But fortunately, I've got a whole bunch of universal hash functions in my pocket that are different. They're cheap, they're simple, they're easy to find. So there's the build phase and there's the match phase. Rest of the build phase, I go through every page of R, I hash it, I put it in a partition. That's gonna be basically, I have to read each page of R, I have to write each page of R. Remember that it's in a different place. There's the hash R, which I read, there's the unhashed R, which I read, and there's the hashed R, which I write. The number of pages in the union of the R sub i's, right, R1, R2, up to R37 or whatever it is, that's gonna have pages of R size in it, even though, but it's the hash partitions of R. So I read R, that's gonna be pages of R, I write the hash partitions, that's gonna be pages of R. Same thing for S. Okay? And now, what about the match phase? If everything fits nicely inside memory, same deal. I read all of R, and I only have to read S once if R fit inside memory. If R fit inside memory. So that's cool. 2 times pages of R plus pages of S plus 1 times pages of R pages of S. It's going to be 3 times pages of R plus pages of S. There are 1,000 pages inside R. There are 500 inside S, so that's where the 4,500 comes from. 3 times 1,500. Okay. Again, things get more complicated if you have to, go to H2, H3, etc. Comparing sort merge versus hash join, given a reasonable amount of memory, we saw that the cost is going to be, 3 times pages of R plus pages of S. So basically, hash join is better if the relation sizes differ greatly because it needs less memory where, again, you can go ahead and use a smaller relation where I used R before. You can use a smaller relation as the one that you're building a hash table from. So, hash join also, as we will see later in this course, toward the end, it's extremely parallelizable, more parallelizable than sort merge is. Parallel is good. Parallelism gets used all over the place like crazy. Because CPU and memory are much cheaper than they used to be. But sort merge is less sensitive to data skew. Too many things going to the same place gets you in trouble. And you've got the same value showing up a lot no matter how many H2, H3s you go to, it won't help. Also, sort merge has this other wonderful advantage that the result of sort merge is already sorted. If you need the results to correspond to an order by, and it's basically what you get out of sort merge, then you save yourself having to do a sort later. So that's an advantage to sort merge. And if you have high skew, I switched to a new slide and I didn't realize it. So sort merge is less sensitive to data skew. Now, again, if you have equalities on multiple attributes instead of a single attribute, then you can do the same things that we've done before. Everything works with multiple attributes instead of a single. So for index and natural join, if you have an index on both of the join columns, you can take advantage of that. Otherwise, if it's just on one of the columns, then you'd have to, do extra checking on the predicate for the other one. So, build an index on an attribute. Remember, you can use index intersection as well to be able to take advantage of things to find all the matches. And basically, for the sort merge, you sort on the combination of the join columns, same thing that we did with one column, but you can do it with two. For hash, same thing. You hash partition on the combination of the two columns rather than just doing it on one of them. Inequalities are painful. They don't show up all the time, but when they do, they're expensive. So basically, if you have a clustered B plus tree index, then you can go ahead and use a range scan on the inner if the inner has a clustered index. So that is really useful if you happen to have clustering index on the inner. But the number of matches is much bigger than with an equijoin. But if you have to do it, you have to do it. And I've seen cases in which people have actually written that and needed to be able to do it. Can't use hash join because hash is not very good on ranges, as we've discussed several times. Block nested loop is likely to be the best thing there. Again, where things not hashable, where we have non-equal sort of predicates. And so we don't have any time left, but this is the last slide. We looked at variations of nested loop joins. We looked at sort merge join, and there are several hash joins that are discussed inside the book, but we've only talked about the brace hash join. Question as we do the exit music.
Sorry, it was just from 2 slides ago.
Yep.
I was just a little confused as to why you didn't factor in loading the R sub I, like the hash partition, back into memory.
I did. That's the match phase. That's the pages of R. Because remember, you're dealing with all the R sub i's. The sum total of the R sub i's is pages of R. That got counted.
Okay.
That's the match phase.
Does that mean, so are we just getting the S and the R from the exact partition?
Yes.
So we're not reading back from the
Not from R. The whole point of creating the partitions is that then we read them all in to do the matching. We use the original R and S to be able to create the partitions, then we use the partitions. We don't have to go back to the original R and S. Important thing. So again, why is the match phase pages of R? Sum total of the pages of RI's is pages of R. Why is pages of S the value in the match phase? Sum of the totals of the pages of S of I is pages of S. Good question. Sorry I didn't mention that. All right, and I think we're done. Friday we will go over lecture 10, which I will post a little later, and that talks about